Assalamu alaikum. In continuation with the previously discussed topics of module 7, in this video we are focusing our discussion on Ranch-Katta method. Ranch-Katta method is basically a numerical method which helps us solve differential equation. This method that we use now was developed by these two gentlemen, Karl Ranch and Martin William Katta. Karl Ranch basically laid the foundational ideas by extending Euler's method. His work focused on achieving higher accuracy than the Euler's method. We have already discussed about Euler's method in our previous discussion. Later, Martin Katta refined and formalized Range's ideas, which eventually led to the classic fourth order Range-Katta method that we use nowadays to solve any differential equations. So in this video, we will look to explore the Ranch-Katta method from the very beginning. First, we will see second order Ranch-Katta method, then we will move our discussion towards the fourth order Ranch-Katta method. So Euler method is the starting point of the Ranch-Katta method that we use right now, and we have already discussed what Euler method is. Euler method is a numerical method for solving differential equation, and by solving differential equation, what do we mean? We mean that using this numerical method, we try to approximate the function y on the graph. And how do we do that? We start with some initial value that is given to us, and then we plot subsequent points on the graph paper using two clues that are given to us. One is the slope of the function that is given to us in the form of first derivative, and then we utilize this equation or the formula. Here all the values are known to us. H is the step size, which is the regular interval after which we are looking to find the value of y. Here we use the slope of the approximated function at this starting point, and following that slope we reach the next approximated value on the graph paper. So Karl Ranch took this method and developed it. He worked on achieving higher accuracy from Euler method, and then William Katta formalized it, and together we call it Ranch-Katta method. Now we will see what they actually formulated. So our discussion will start with second order Ranch-Katta method. Why it is called second order Ranch-Katta method? Because it has come to this version using Taylor series and up to the second order term of the Taylor series. That is why this equation or this function is called second order Ranch-Katta method. The main idea here is the same, like what was the main idea of Euler method. We need to approximate the function y in the graph paper, and in Euler method we used this formula for approximating certain values of y in the graph paper. In second order RK method we will use this function to approximate values of y in graph paper. Here we can see there are terms like a1 k1, a2 k2. They themselves defined these values. K1 is f of x I y I, which means the point where we will be starting, the slope of the approximating function at this point is k1, and k2 is defined as this. So here we have found few other unknowns as well. Okay, from here let's take the formula of second order RK method. So Karl Ranch and William Katta developed this formula to approximate function from any given differential equation, and here there are few unknown available. Okay, these unknowns they have defined themselves. These unknowns should have this relationship between them, and if these unknowns have this certain relationship between them, then we can say that this formula or this function is applicable for second order RK method. This is the generalized form of second order RK method. This generalized second order RK method can have many variants, and we have already discussed about one of the variants. Let's see how. Let us summarize what we have said so far. Second order RK method is another numerical method that helps us approximate the function y from any given differential equation, which means if we are given a differential equation and we are asked to solve it, it eventually means that we are asked to calculate the function y. So using numerical methods, we will solve for y using intuitive method. How we can do that? We can approximate the function y in graph paper. In order to approximate the function in the graph paper, we need points in the graph, and using this formula we can find few points, and then if we connect them, we will see that it matches closely with the original function. So second order RK method gives us this formula. In this formula, we know how the K1 and K2 behaves. Now we are talking about some variants of RK method. The first variant that we are going to talk about, if this relationship holds, if A2 is half for any second order RK method, in that case, if A2 is half, we plot A2 here, which eventually means the value of A1 will be half. If A2 is half, then if we plug this value here, that means that P1 and Q11 will be 1. So as a result, if this happens for any second order RK method, it actually turns into Hume's method. And we have already discussed about Hume's method. If you remember, in Hume's method, we calculated the next value of y from the initial value using this formula, where k1 is f xi yi and k2 is f xi a plus h yi plus k1h. Okay, what does it mean in the graph? Let's see now. If you remember that Hume's method is an iterative method of approximating function y from a given differential equation, and there we use this formula where k1 is this and k2 is this. Now let us see it in graph paper. Let's assume this is the function y that we are asked to calculate, and this is xi and this is xi plus 1. This is the yi. Let's say this is the initial value. So for Hume's method, how did we reach to the next yi plus 1? If you remember the Hume's method, we calculated one slope at this point and we calculated another slope at the next available point, and then we took an average of those slope and plugged that into the function to calculate the next value of y. Okay, let us see what does it mean in the graph paper. So we have this initial value at our hand, and if we plug this coordinate into the function, that will give us k1, which is the tangent of the function available at this point, and this is k1. Using this k1, we can reach to this point which is available at xi plus 1, and the coordinate of this point is obviously xi plus 1 or xi plus h and yi plus k1h, as we have reached here using k1. Okay, now if we plug this coordinate value into this function, that will give us k2. K2 is basically this slope. Now what we can do, we can take k1 here and plug here, take k2 and plug it here, then take the average of these two slopes, multiply it with h, and then add it with previous y. In this way we can get to the next point which is available on the graph at this position. So this is how, using Hume's method, we can move forward at regular interval of x. We can get our corresponding value of y, and after getting subsequent amount of points on the graph, we can connect them and see how closer it went with the original function y. The bottom line here is that the Hume's method that we applied or discussed previously is eventually a RK method of second order. So the main idea here is that second order RK method can have different variation depending on how we set the relationship between the unknowns that are associated with the original RK method's formula. For this case, we assumed A2 to be half and then everything fall into places. In the similar fashion, if we set some other values to some unknowns there, we can get another variant of second order RK method that we will see next. If we assume the value of A2 in second order RK method to be 1, then correspondingly the value of A1 becomes 0 and the value of P1 and Q11 becomes half, which lead to a new variant of second order RK method that is called midpoint method. The formula of midpoint method of calculating next iterative value of y becomes this, that yi plus k2h, so which apparently would mean that we will not need k1 but we will need k1, as k1 is f of xi yi and k2 is f of xi plus half h and yi plus half k1h. Let's see how midpoint method pans out in the graph paper. Let's assume this is xi and this is yi and this is the interval, so this is xi plus I plus 1 or xi plus h. As we know, if we draw a tangent at this point and the value of the slope will be k1, and if this was Euler method, this point would be our next iterative point, as this is k1h yi plus k1h, but we need this point xi plus h by 2 yi plus half k1h. If this is yi plus k1h, so this point has the coordinate of xi plus half h yi plus half k1h. If we plug this value into this function, that will generate another slope. This is k2. Okay. Now at our hand we have k2. To reach to the next value of y, we need yi plus k2h. So how do we find k2h? We need to bring this k2 here and following this path we can reach here. This is k2h and this is actually our next iterative value. So using midpoint method, this is how we try to find out the next iterative point on the graph, which is a bit different than Hume's method, and in formula this is how it looks like, and in graph paper this is how it pans out. So this was the discussion about second order RK method. So using second order RK method, we have seen how we can find out values of y of the function that we are trying to intuitively plot in the graph paper. It's very easier to do the mathematical problem by plugging the values into the formula, but our goal should be to understand what we are doing when we are using these formulas and calculating values. So that was my priority, to let you understand what goes behind the formula. So this was the discussion about RK method and the discussion about second order RK method. In the next part of the lecture, we will see how RK4 method works